Alright, now I'm recording. Alright, anything else? Alright, so I want to pick up some stray topics. I want to talk about indirect file addressing, and then time permitting I want to start talking about floating point. I'll post homework today, which will be due on Tuesday, and it will cover whatever we get through today. So assuming we do indirect file addressing, it'll have that on there. If we don't get through floating point, I won't give you homework questions on it. But again, Tuesday, I'll probably lecture most of the 4 hours because labs should be done by Tuesday at noon, so we don't need the lab time. And I want to get through, there's actually 4 more chapters of the book that we haven't started yet. And I usually try to do those in 1 or 2 classes. They are material that probably won't be on the exam, but I want you to have been exposed to it here anyway. So we'll do that, and then if there's any sort of wrap-up questions on Tuesday for the final, we can talk about those also. So let me fire up MPLab. Alright, well let me talk about the easier one first. There's this config statement that we see in the top of our code. And it usually says something like config WDT equals off. And then maybe LVP equals on, and there's something for oscillator control and so on and so forth. Config is a different type of instruction. Alright, so we've got a number of instructions. We've got things like clear file register 80. Okay, that's an assembly language instruction. That translates into machine code 1s and 0s, and that gets loaded into the memory of the PIC processor. We've also got things like origin, EQU, include, and so on. Those do not translate into assembly language. They do not get loaded into the PIC processor. They don't get loaded into the hardware. They affect how the assembler in MPLab treats our assembly language code. Right? So I write clear F80, where should that get loaded into memory? Well, it depends on the origin statement. I say clear file register count, where is file register count? Well, that depends on an EQU statement. So these are directives. These don't translate into 1s and 0s. These are instructions. These do translate into 1s and 0s, and they get loaded into the memory, the program memory of the processor. Config is kind of a third type of statement. Config is generating binary information that gets sent to the processor. It does not load into the program memory. It's not an instruction. It's not something that's going to be executed because the program counter is pointing to it. But it basically conditions the hardware to act in a certain way. For example, when we config and we say oscon equals, we're telling the PIC processor something about what the oscillator speed should be, what the clock speed should be. When we say config LVP equals off, we're saying we don't want to allow low voltage programming. So these do affect the hardware, but not in the sense of being instructions that get loaded into program memory. They control the configuration or the nature of the physical hardware. And the one that I want to make sure that we talk about is WDT equals off. And every piece of code that we have, you'll see this in the beginning. Config WDT equals off. Okay, WDT, that's the Watchdog Timer. So what is a watchdog?
Stays on alert? I don't know.
Yeah, I mean it's usually a mean or supposedly mean dog that's left on a property somewhere so that if somebody walks by, the dog wakes up and starts barking and snarling and it scares a person away, right? It's something that's hanging out in the background, doesn't really affect anything until some event occurs, until something wakes it up. And then when it wakes up, something spectacular happens. Okay, if you've never seen a watchdog, find a junkyard somewhere and walk by. You'll see what a watchdog is. So there's a little tiny watchdog inside the PIC processor. Okay, and what this watchdog is doing is it's sleeping. It's just hanging out. It's having a nap. But after a certain amount of time, a little alarm goes off and it wakes up the watchdog. And when the watchdog wakes up, it freaks out and it resets the processor. Okay, so the watchdog is normally asleep. After a little bit of time, once the power comes onto the chip, after a little bit of time, an alarm goes off, the watchdog wakes up, resets the processor, and goes back to sleep. Alright, what is the use of this? This is useful because suppose you have a piece of code that's doing something mission critical. Okay, let's say it's monitoring a system or it's controlling the temperature in a room. And there's a possibility that your code is going to get hung up somewhere, that something will go wrong, something will glitch out, who knows. So maybe you've written your code and it's supposed to, you know, take a temperature reading, turn the thermostat up or down, whatever. And if that code were to not run, your room would overheat and all the stuff that you have in that room gets ruined. Let's say it's a refrigerator room. So you really want to make sure that your code does not get hung up somewhere. So you use a watchdog timer. So we don't configure the watchdog to be off. We let the watchdog run. And let's say your main program looks like this. So you've done some setup and such. And so what are we going to do? Check temp. Adjust it. And go back up here. So some simple loop where we're taking some readings, doing some things, or whatever, right? And we expect our program to be sitting in this loop. Okay, what we do is we add an extra step in here, which says clear the watchdog timer alarm. Reset that alarm clock that's supposed to wake up the watchdog. So there's an instruction for doing that. And every time we execute that instruction, the alarm goes back to 0. It restarts the period before the alarm goes off and wakes up the watchdog. Okay, if our code is working correctly, if we're executing this instruction frequently enough, the watchdog will never wake up. Because every time we come through here, the alarm gets reset. But if something happens, if some condition we didn't anticipate takes place, and we end up somewhere over here in some, big long loop, enough time passes that we haven't cleared the alarm goes off, the watchdog wakes up. What does it do? It resets the processor, and we go back to the beginning. And in the beginning here, we can put in some code to check to see if we just got here because we just powered on, or if we got here because the watchdog reset. And if we got here because the watchdog timed out, right, then we can, send a message to someone and say, hey, something's wrong with the control system, send someone over to check. So it's a safety measure. And it's really common in all of these types of systems that are meant to be used in, say, embedded applications. It's a safety check. And, every now and then you're using your laptop and what happens, it suddenly freezes up, right? Well, same idea. If your laptop stays frozen for more than a minute, what do? You reboot it, right? So you're doing the role of a watchdog timer yourself. While you're sitting there, you keep doing things on your laptop, and at some point, if it stops responding, you go ahead and you reset things. So that was one. That was one thing I wanted to talk about. So you can read about these things in chapter 19. This talks about the configuration bits, right, which are the things that the config statement feeds into. And it talks a little bit about the Watchdog Timer and the oscillator controls and so on and so forth. And there's a series of locations that you can control, right, these different configuration registers. This is outside the regular file registers. This is outside the program memory. This is a totally separate chunk of memory, right? And you can use this to control the Watchdog Timer and other things. And there's a fancy picture of how the timer works. And again, it's based on the instruction clock, and you can adjust what the time interval is before the timer goes off, and so on and so forth. And if you go down to, well, let me take our quick guide. So clear Watchdog Timer, clear WDT. That's the instruction used to reset the time interval. All right, so that's one thing. The other thing I want to talk about is the rotate instruction. I'm blanking on the opcode. Nope. So byte-oriented instructions, there's a rotate left carry, rotate left no carry, rotate right carry, rotate right no carry. So let's just take a look at these. Okay, real simple jump code here, right? I'm going to take the number 1, I'm going to load it into file register 80, and then I'm going to do this instruction RLNC80. And I want to just look at what that does. So I'm just going to add a watch here for file register 80. And I'll put a breakpoint right here. And build this and run it. Alright, and so let's look at our variable here. File register 80 has a value of 0. I'm going to put a 1 in there to start. Okay, so I want to look at the binary value. It's 7 zeros and a 1. Rotate left no carry file register 80 will do the following. Basically shifts that 1 over 1 spot. If I do the rotate left again, it shifts it another spot. If I go ahead and I don't know, let's make this register equal to 101, and I do a rotate left no carry, it makes it a 1010. And every time I do this, it shifts it over 1 spot to the left. And now there's a 1 in that most significant bit, and if I shift that bit over, it disappears. and it comes back on the right side. And then if I do an 1/8 rotate, I'm back to my original number, 101. Alright, so we have an 8-bit file register. We say rotate left, no carry. Each bit just moves over one spot. And the most significant bit moves over to the least significant position. Now, almost every processor you encounter is going to have rotate instructions. Some of them will also have a shift instruction. The only difference between a rotate and a shift usually is a shift doesn't do this. If you do a shift, the bit that's at the end here just disappears. But with rotates, the last bit moves back over to the right.
What's meant by the no carry?
So let's change this to a carry. And we'll start with a 1. Okay, we're going to look up here at, let me go ahead and, I don't know what's going to be easier here. Probably easiest is to look up here at this carry bit. Okay, so this lowercase c up in the upper right, that's a 0. Okay, it means the carry bit is 0. So I'm going to rotate this 1 bit. So now it's in the 2nd position, it's in the 3rd, 4th, 5th, 6th, 7th, 8th. Okay, with a plain old rotate no carry, if I rotate this again, that 1's going to move over to the rightmost position. But rotating with carry, that 1 disappears and it goes into the status register. It goes into the carry bit of the status register. And then on my 9th rotate, that carry bit goes into the register that I'm rotating. So the whole difference is this. Let's see what the I just want to be accurate about which bit the status bit uses for carry. It's the least significant bit. So same thing when you rotate left through carry, each bit moves down 1 position. But this last bit goes into bit 0 of the status register, and the old value of bit 0 goes into the rightmost spot on the thing you're rotating. So you get that kind of effect. So it becomes a 9-bit rotate, but it also means we can easily rotate 1s or 0s into this register by setting or clearing this bit of the status register. And so it's a way to build up a bit value in a register by modulating this 1 bit and rotating. And then there's similarly rotate right, no carry, and rotate right carry. And so we used a swap instruction to move the high 4 bits of a number into the low 4-bit positions. We could also have said rotate right, no carry 4 times. We could also have said rotate left, no carry 4 times. But swap F is easier. Alright, so that's an instruction you'll see in pretty much all processors, and we didn't have to use it in this course, but again, I want to make sure people have seen it. All right, questions on those? All right, let's take 5 minutes. We'll come back. We'll talk about indirect file addressing, and then I'll let you get to your lab. So I'll be back in 5 minutes. All right, somebody shout if you can hear me.
Hi.
Cool.
Hi.
Perfect. All right, so I believe everybody here has taken CSE 121, and a number of you have taken 224, which means you've at least had some exposure to the subject of pointers. And we're going to talk about pointers in assembly language. And this can actually really help with understanding what's going on in C or other languages. It's generally helpful if you can go down to the hardware level. That can make it easier to understand what's going on at a higher software level. So I'm not going to get bogged down in the syntax of C. I'm going to do this strictly from the point of view of pick assembly language, but I will reference some C statements along the way. If you're not comfortable with pointers in C, don't worry about the C references, okay? I'm going to put them in to help people who are comfortable with those, but you don't need to know C pointers, okay? But hopefully you've seen them at least once before. So let's look at a set of special function registers. These are called file select register 0 high, file select register 0 low, indirect file register 0. Okay, first thing I want to be really clear about, there are 3 sets of identical registers. There's also an FSR1H, FSR1L, INDF1, and there's an FSR2H, FSR2L, and INDF2. They work identically to each other. I'm going to mostly talk about the bank 0, okay? But there's 3 completely independent but identical sets of these indirect file registers that we can use in the PIC processor. There's also other registers. There's POSTINC 0, pre-INC 0, POSTDEC 0, plus W 0. There's a bunch of these. We're going to deal with these first 3 primarily. But let me show you where these pop up. So if you look down at the end of the quick reference sheet and look at this table of special function registers, you'll see, for example, INDF 0, POSTINC 0, POSTDEC 0, pre-INC 0, plus W 0, FSR 0H, FSR 0L. Okay, that's the whole bank of registers associated with this first set of indirect file registers. And then here's all the ones corresponding to bank 1. And then a little later, here's all the ones. Sorry?
I don't think we can see your screen. You're showing the register.
Okay. Interesting. All right, that should be better.
There we go.
All right, cool. So yeah, so INDF 0, POSTINC, POSTDEC, pre-INC, plus W 0, FSR 0H, FSR 0L, right? A whole bank of registers associated with indirect registers, pointers basically, and then a whole second independent bank, right? Bank 1, and then another bank, INDF 2, down to FSR 2L, okay? I'll mostly deal with these 3 registers, and mostly I'll deal with these 2. All right, really simple behavior here, but can be complex to use. FSR 0H and FSR 0L. Well, Well, these are each 8-bit registers. Together, they form a 16-bit register. And these 16 bits correspond to a location in the data memory. In other words, a file register number. So for example, I could load a 0 into here, and for most of what we do right now, FSR0H is just always going to be 0. But FSR0L, I can load, you know, some interesting value in. So let's suppose I load 0010 into this pair of registers. Okay, so far it's just a pair of 8-bit registers. This one has 00, this one has 10. So I move 00 into W, move W into FSRH, move 10 into W, move W into FSR0L. Nothing weird going on there. Okay, once I have done that, INDF 0 is a reference to file register 10. So INDF 0 is really special. Anything I do to INDF 0, I am going to end up doing to file register 10. Why is it file register 10? Because that's the value in this FSR0 H&L register pair. If I change FSR0HL to be 20, then anything I do to INDF 0 will be done to file register 20. It's an indirect register. If I say clear file register INDF 0, I don't clear this register. In this case, I would clear file register 10. Okay, let me throw my first view of C out here. Again, if you're not comfortable with this in C, don't worry about it. INDF 0 is a thing pointed to by file select register 0. Okay, so let's just look at this in some code. Alright, pretty short test program here. I'm going to put a 55 into W, and I'm going to say let's move W into INDF 0. And then I'm going to go back to loop. Alright, I'm going to look at a few variables here. I'm going to look at FSR0H. I'm going to look at FSR0L. And I'm just going to look at a few file registers. And I put a breakpoint right here at my loop. Alright, I'm about to say move W, which is 55 hex. I'm going to move W into INDF 0. What do you anticipate is going to change in my list of variables once I execute this move WF instruction?
Maybe decrement somehow. I'm not sure.
So I'm going to move 55 somewhere, right? Because that's the value of W.
It's gonna go into 0, 0.
It's going to go into file register 0. Even though I'm moving it into INDF, which has, you know, some location F something something in program memory, it doesn't actually move it into that location. It moves it into, in this case, location 0. Why? Because FSR 0, L, and H are 0, 0. So this one instruction, move WF INDF 0, loads a 55 hex into location 0. And if I keep executing it, it keeps loading 55 into there. Okay, now suppose I change FSR 0L to be 4. Now when I move WF into INDF 0, what do you think is going to happen?
INDF 0 be 4.
This is true. What's going to change on my list of variables here? Anything?
WReg is gonna go into 4.
It's going to go into file register 4, right? File register 4 is currently a 0, but FSR 0 has a value of 4. So INDF 0 means file register 4. So this is basically saying move WF into file register 4. And bingo, file register 4 changed to 55 hex. Now if I change FSR 0 to be 2, and I execute that same instruction, where does the 55 get loaded? File register 2. If you understand what just happened, then you understand everything there is to know about pointers. So if you don't understand what just happened, please ask some questions.
So when you're setting the FSR, in what context does it play if we were to set it up inside the code? Because I mean, right now we were just inputting values directly into it in the variables.
Okay.
But how would it reflect like if it was outside of the loop?
Good question. So let's, in our code, set FSR 0, H, and L to be 0. And I'm going to put this inside. So I'm going to put 55, I'm going to load it into INDF 0. And then I'm going to make a change to FSR 0L. I'm just going to increment it. And then I'm going to branch back to my loop. So let me rebuild that. Let me start executing. Okay, FSR 0L is 0. I'm going to put a 55 into INDF 0. So location 0 gets set with my magic bit pattern. The next time I do that move F, it goes into file register 1. The next time is file register 2, file register 3, file register 4, file register 5, and so on. I'm loading values into successive file register locations. And And I'm doing that simply by moving into INDF 0, but changing what FSR0L is. All right, questions about that?
Does INDF 0 have like a physical place in the memory?
That's a really interesting question. So if you look at INDF 0, there's a little footnote next to it too. Footnote 2 says this is not a physical register. So no, it doesn't. There's actually a gap in the memory where all of these special function registers are stored. There's no set of flip-flops, there's no register corresponding to address FEF. It's intercepted by the hardware, effectively, which says, oh, I don't want to actually clear location FEF. Let me look and see what's in FSR0L. Oh, it's a 5. Okay, I'm going to move this into location 5 then.
So when does FSR0H play a role in where things go?
So for our processor, it doesn't, because we only have 256 file register locations, unless we wanted to tinker with one of these special function registers. So if I wanted to set the value of port A, for example, I could set FSR0H to be F and L to be 80. And well, let me pick on something that I know I can write. Let's suppose I wanted to set up T2 con. So T2 con, or T2 timer 2. So FCC. That's timely. All right. So let's put a hex CC into FSR0L. And let's put an F into file register 0 high. Okay, so that's the address of this timer 2 register. So let's go ahead and look at timer 2. And now I'm going to rebuild and simulate. Okay, so FSR0H and L has been set to 0FCC. Timer 2 is 0, that's just the default value it started at. Its address is FCC. So now I'm going to move 55, which is in the W register, into INDF 0. And guess what? Timer 2 got changed to 55 hex. So,
Okay, that's much clearer.
Okay, cool. So for most of what we do, we really only use FSR0L, but on a larger processor with more file registers, we could use H and L together. And if we want to hit something at the top part of our address space, the F such and such registers, we can set FSR0H to an F. All right. So we got FSR0H, FSR0L. We use these a lot, and we find ourselves writing this kind of code over and over and over again. So there's a special instruction we can use to load a value into the file select register. It's called Lfsr. I don't seem to be able to search in this PDF. So it's a literal instruction, Lfsr, and we tell it which bank of indirect registers we want to load this for. So we can say Lfsr 0, 1, or 2, and then we can specify the full 12-bit address that we want to load into that file select register pair. So this is our last 2-word instruction, like go to and call and move FF. It takes 32 bits to code up this instruction. Why? Because we need 12 bits of literal information, and we need 2 bits to say, are we loading FSR 0, 1, or 2? So all of this that we did up here, we could have done simply by saying load file, select register 0, 0x FCC. And so we're starting off, well, FSR 0L happened to have a CC in it, but once we execute this LFSR instruction, that loads both file register 0 high and file register 0 low. So LFSR takes 2 arguments. The first is a 0, a 1, or a 2, and the second is the 12-bit value you want to load into that. So that's a really useful way to initialize these file select registers. And then once this is initialized, INDF 0 equals the file register pointed to by FSR 0 high and low. Okay, it's indirection. It's saying don't clear INDF 0, don't clear FSR 0, FSR 0 L or H. Look in here to find an address. Clear what's at that address. If I say clear INDF 0, if I say increment INDF 0, don't increment this, don't increment these. Look in here, see what's stored in there. That's the address of the thing that you want to increment. Alright, if you come under Window, Target Memory Views, File Registers, you can get a different view of the file register memory. And this can be useful when you're playing around with indirect addressing, because it shows you all of the contents. So this is address 0, 1, 2, 3, all the way out through F. The next row is address 10, 11, 12, all the way out through 1F, and so on. And for us, this ends at FF. But, you know, for a processor that had more memory, it could contain all of these other locations. They're missing on the PIC 18F1220 until you get to F80, and now we have the values for all of our special function registers. So now if I run this code, and I look at my file registers, I can just keep running from breakpoint to breakpoint, and you can see it's loading up our memory with 55s. And it'll just keep doing that. If I take out my breakpoint and just let it run for a while, and then pause it, my whole memory got filled up with 55 hex. And probably some of my special function registers that I shouldn't have loaded. There's a 55 down there. Alright, so that's basically all there is to indirect addressing. But there's lots of other things we can do with it. But I want to ask again for you to come back with questions if any of this is not clear.
Going back to the previous part about INDF increment and incrementing, I think, what was it, FSR 0L.
Mm-hmm.
How would we lecture. I mean, could we just cover that bit of portion of the lecture again?
So say that last thing again.
Could we go over that portion of the lecture again? I just didn't really get the full context of it.
Well, all I'm doing here is incrementing FSR0L.
No. I'm talking about the previous one, the previous example before this. The one that you were writing down on paper.
Okay, let me see. So this is what I was writing on paper.
I believe it was like the next one. It was something about INDF 0,
Mm-hmm.
I believe. I think. I kind of lost my thought.
Is it the LFSR?
Yeah, something like that.
LFSR? So LFSR was the thing we were just doing where we said we could load FSR0, H, and L with a single instruction.
Okay, alright.
Right,
Yeah.
so if I do like FCC or F80, right, that'll load 80 hex into FSR0L, and it'll load F into FSR0H. So it's a shortcut of, it's a shorthand version of doing these 4 instructions where you push something into FSR0L and H by hand.
Alright.
Cool. So if we were going to deal with more locations than just our 256, right, this code doesn't actually work. I'm incrementing FSR0L. Once FSR0L is FF, once I'm pointing to this last location in memory, when I increment it again, what does it do? It rolls over to 0, and now I'm back to my first location in memory. Right? Incrementing FSR0L does not increment FSR0H if it rolls over. So if I wanted to, you know, I could check to see if FSR0L was now 0, and I could say branch if it's not 0, back to loop. Otherwise, I could say increment FSR0H and then go back to loop. So this program will go through and it will dutifully write a 55 into every file register that it has access to. Now all the ones in the middle, when I try to write to those, it's a no-op. It doesn't do anything. But when my high register gets up to 15, it's going to start writing values into here. And it's probably going to do something really bad to the machine, because you don't want to just throw random values into special function registers, because these affect interrupts and you know, timers and all kinds of things like that. But just for kicks, let's just see what this does. Let's just, yeah, so I don't have a breakpoint, so it's just running. Well, it didn't seem to do anything too terrible, but you can see a lot of my special function registers got loaded with 55. And who knows what I've done now to my poor PIC processor, because you're changing the tri-state bits and the output bits and all that. But this works, right? It will do whatever you tell it to do. All right, other questions on the underlying mechanism? Because there's a lot of other things we can do with this, but it's just going to be adding details to what we've already done. So this basic notion of INDF is a reference to whatever this file register pair is pointing to, right? Questions about that?
What does the 0, 1, or 2 do after LFSR?
Totally separate set of registers. So for example, I could say let's load file select register 1, and now I could say go into indirect file register 1, and let me get rid of this stuff and put my breakpoint here. Right, so now I'm loaded a 1 into file select register. Let me do this. Let me put a 1 into file select register 1. Okay, FSR 0 is still C9, right? But I'm not using FSR 0, I'm not using INDF 0, I'm using INDF 1. So I'm going to move a 55 into INDF 1. What's going to decide where it gets written? The value of file select register 1, which I've just set to 0. So this will put a 55 into file register 0. And, well, I should increment file register 1. If I don't increment file register 1, then this just keeps writing location 0. And I'm changing file register 0L, but that has no effect. So it's 3 completely separate, independent sets of registers, right, which are just indexed by 0, 1, or 2. So instead of moving something in FSR 1L and FSR 1H, I can say LFSR 1. Instead of saying FSR 2L and FSR 2H, I can just say LFSR 2 and put in the value I want to load. All right, let's take this further. Let's copy stuff from one file, from one chunk of memory to another. Okay, we've already seen we can initialize a bunch of memory by just making a loop and writing to INDF 0. Let's copy some file registers from one spot in memory to another. So I'm going to make a setup function which is going to load some interesting values into a chunk of memory. So this is the person behind the curtain. I really hope I didn't make any typos other than that one. Alright, this is test code. By the way, I posted a video Tuesday night on the 270 playlist. It's called How to Play Around with MP Lab. It's basically doing this kind of thing, but looking at two things. I think I was looking at timer code, and then I was looking at using pulse width modulation, using the whole ECCP subsystem. It's like 10 or 20 minutes, but it basically does the kind of thing that we're doing here. You've got some concept that we've learned and that you're trying to understand. How can you sit down with MP Lab and use the software itself to help you understand these concepts, right? This is exactly what we're doing right here. I want to give you some examples. I can write code on paper and tell you about it, but let's actually use it in the simulator. So I put together a video sort of demonstrating that. If you haven't watched it, I recommend taking a look at it. Like I say, it's 10 or 20 minutes. But you'll hear me say a lot, especially if you're doing the 200 CS sequence with me. You'll hear me say a lot, get your hands dirty, right? Get in there and start playing with the stuff. And this is what I mean in the context of Engineering 270. So I'm just writing some code here that's going to put successive values starting from 0 into a bunch of memory locations from 1, 0 through 1B, just so I have something to work with. So I'm going to build that, and I'm going to run it, and I'm going to look at my file registers, and you can see starting at location 10, you know, I've put successive numbers 0, 1, 2, 3 all the way up through B into those locations. Alright, so what I want to do is I want to copy from a chunk of memory starting at location 10 to location 40 for no particular reason. Okay, so what am I going to do? Load file select register 0, 0x10. This is where we want to read from. And I'll just use file select register 2. This is where we want to write to, or this is to where we want to write. And then I'm going to make a loop. Move F, INDF 0, W. Let's read from wherever FSR 0 is pointing, which is going to start at location 10. Put that in the W register, and then move WF, INDF 1. And my comment here is copy from angle bracket INDF 0 to angle bracket INDF 1. Angle brackets are often used to say the thing at this memory location, right? Don't copy from INDF 0, but copy from, let me change this. Copy from file select register 0 to file select register 1. We're not copying FSR 0 to FSR 1, we're copying the memory contents whose address is given by FSR 0 to memory at the address given by FSR 1. So this pair of instructions, the first time I run, should copy from file register 10 to file register 40, which is going to be uninteresting because they're both 0. But then I'm going to increment file register FSR 0L and FSR 2L. And I'm going to go back to my loop. So 5 lines of code. And each time I execute these 2 lines of code, I should be copying from one location to another. And then these 2 lines are going to change what those 2 locations are. So the first time through I'm going to copy from 10 to 40 because that's what I initialized my file registers to. And then the next time I'm going to copy from 11 to 41 and then 12 to 42 and so on. So let me put my file registers up here. And let me put FS2 on my watch list.
So I'm kind of confused.
Okay.
Is, you're referencing FSR2 in some places and then FSR1 in other places.
Thank you. Thanks.
Yep.
And I could have done 1 if I was consistent, or I could do 1 and 2 if I was consistent. So I'm just doing 0 and 2. All right, so let's run this. We've built it. Let's go ahead and start executing. We've initialized file register starting at 10, file register starting at 40 are all 0. Okay, so we're going to load FSR 0 should get loaded to 10 hex. So this number down here, which is D1, that should change to 10. And then FSR2 we're going to set to 40, so FSR2L, this 55 down here, that should change to 40. Okay, these are pointers. And now we say take the thing pointed to by FSR0, move that into W. So this first time through is uninteresting. But let's increment FSR0L, so that's 11, and FSR2L is 41. Okay, now INDF 0 refers to the contents of file register 11. And I'm going to move that into W, and you can see up here W changed to 1. And I'm going to move W into INDF2. Well, INDF2 refers to file register 41. And so file register 41 should become a copy of file register 11. And there it is. And the next time through, we copied file register 12 to file register 42. And the next time through, we copied file register 13 to file register 43. So we're moving a chunk of memory. Right? In this case, we're moving a bunch of bytes starting at location 10 to memory starting at location 40. Is this still making sense? Alright, so you're going to have a bunch of homework questions on this, and I'll also post a different view of what's going on here. But let's go into some of the more subtle aspects of this. So we know about Lfsr, right, which we can use as a shortcut. This is also something we do a lot. We use a file register, and then we want to add 1 to it. So there's another special function register, which is called POSTINC 0. This is exactly like INDF 0, but after your instruction finishes, add 1 to FSR0 H and L. Okay, this is like this in C. Take FSR0, find the thing at that address and do whatever you want to do with it, and then when you're done, increment FSR0. Okay, it's a post increment. We use the thing that's pointed to by FSR0 H and L, and then when we're done, we increment that 12-bit number, which means if FSR0 is L and we do a POSTINC, FSR0 will overflow from FF to 0, and FSR0H will get incremented. So it's a 12 or 16-bit addition. So we could do this instead. We can move from POSTINC 0 into W and then move W into POSTINC 2. And that's going to not only do the indirect accesses, right, copied from the thing pointed to by FSR0 to FSR2, but it's also going to increment these two pointers at the same time. So build that and run it. Initialize FSR 0 H and L. So there's our 10 and 40. Okay, so one instruction, I'm going to move the contents of FSR 0's, the thing it points to, into W. But after I do that, FSR 0L automatically increments to 11. And now I take the W register and I copy it to file register 40, and the POSTINC says, and go ahead and increment that to 41. So each time I execute those two instructions, I copy another location from the bank at location 10 to the bank at 40. Now if I wanted to, I could make this even simpler. You can do a single instruction, move FF from POSTINC 0 to POSTINC 2. And now each time I do that move FF, I move another value from location 13 to 43, 14 to 43, 44, 15 to 45, and so on. Right, so right now my file select registers are 15 and 45. This instruction is going to do a bunch of stuff. It's going to read the contents of file register 15. It's going to write that to file register 45. And then it's going to change FSR 0L to 16, and it's going to change FSR 2L to 46. One instruction, you'll see all three of those things happen. So that changed from a 0 to a 5, that bumped to 16, that bumped to 46. All right, more questions? All right, so what do we have in here to play with? We've got INDF 0, that's the indirect. We have post increment, post decrement, pre-increment, and plus W0. So let's just look at post decrement. So I'm going to initialize my file registers to 10 and 40. But now I'm going to move from POSTINC 0 to POSTDEC 2. Okay, first one's going to be uninteresting because it's going to copy a 0 to a 0. But FSR 0 incremented to 11, FSR 2 decremented to 35. Which means the next time I do this move FF, I'm going to copy from file register 11 to file register 3F. And my source, FSR 0 incremented to 12, my destination, FSR 2 decremented to 3E. So now I'm copying from one chunk of memory to another, but I'm reversing the locations that I'm writing at the destination. I'm reading from 0 through these increasing values, but I'm writing starting at 3F and going down. Is that useful? Well, maybe. I mean, if you wanted to write something to reverse a string, maybe, but it's just an illustration, right? It's an example. And let's finally play with pre-inc. So pre-inc, same thing, start with our registers at 10 and 40. But this move FF, what it's going to do is it's going to increment FSR2 before it uses it as an indirect register. Okay, first time through is not interesting because we're just copying a 0. But the second one, FSR0 is 11. We're going to read from file register 11, which is a 1. We're not going to write in file register 41. Even though FSR2 says 41, the pre-inc says before you write, increment this. So it's actually going to write from file register 11 to file register 42. And the next one will read from 12 and write to 43. read from 13 right to 44, and so on. All of these things translate directly into useful stuff in C, right? So POSTINC looks like this. Pre-inc says first increment FSR 0 and then use that as a pointer. POSTDEC says first use FSR 0 and then subtract 1 from it. The last one is plus W0. Does not change FSR 0, but it takes the contents of that file select register, it adds the contents of the W register, and it uses that as the address of your operand.
So it adds it before it does the operation.
It adds it before it does the operation, but it doesn't change any of these variables, right? FSR 0 is unchanged, W reg is unchanged. But again, if FSR 0 happens to overflow, if the low part would be bigger than FF, right, it'll adjust the high part as needed. So here's yet a different way that we could do our bulk copy. So we'll use W as an offset into the memory block. I'm spelling it wrong. Nope, that's W0. So I'm going to move from plus W0 to plus W2. And then I'm going to increment W and go back and do it again. So here's our file select registers. We'll initialize those with Lfsr commands. So FSR0L is 10. That's the starting address of our source memory block. FSR2L is 40. That's the starting address of our destination memory block. And I'm going to initialize W to 0. And I'm going to move from plus W0 to plus W2. Well, that didn't do anything because it's moving a 0. I'll increase W to a 1. You can see the value up here. And now when I move from plus W0 to plus W2, it copies from file register 11 to 41. And if I keep doing this, it'll move successive locations. If I wanted to copy every other memory byte, and maybe I wanted to start from the first one, right? I can rebuild, I can execute, I can initialize my file select registers. Well, FSR0L and FSR2L are still 10 and 40. Those are never going to change. But my W register is 1, so this is going to copy from location 11 to location 41. And there's our new byte. And then I'm going to increment W by 2, so now W is equal to 3. And now when I do my move FF, I'm going to copy from FSR0L is still 10. 10 plus 3 is 13. 40 plus 3 is 43. I'm going to copy from location 13 to 43. This byte right here should change to a 3. There you go. And now I'm copying every other byte. This is also how structures work in C. This is also all how arrays work. If you had an array called X and it was an array of bytes, and you want to access, let's say, let's say at file register 10, this is where your X array is stored. So this is X0, X1, X2, X3, and so on. And now you want to say something like, you know, so this is pseudocode C code, print X bracket 2. Well, how does the CPU find this element of this array? Really simply, first it has to know where the array X begins in memory. Well, that's been compiled into your executable program. It knows that X starts at location 10, and since you want element 2, it should find the element at the starting address of X plus 2, and it should pick off whatever's at that location. So it would take this, and you could load that into FSR 0 and then use INDF 0. And then if you want X bracket 5, you could take the starting address of X, add 5, load that into INDF 0, into FSR 0, and then use INDF 0. But the easier way to do this is to just take the starting address of X and load that into your file select register, and instead of changing that, use this plus W0. So put a 2 into W, plus W0 will now refer to the thing at this location, that's X bracket 2. Put a 5 into W, plus W0 now refers to the thing at this address, which is X bracket 5. So if you write code in C and compile it down to a PIC, you'll see these plus W instructions used throughout every time that you try to access an element of an array. By the way, this is really close to the heart of why arrays and pointers feel like the same thing in C. They really are the same thing. Because at a hardware level, accessing an element of an array is really looking at the address of an array, adding some offset, and then using that as a pointer to the thing that you want. This is why we declare arrays as, say, integer star or character star. So you can really kind of like rethink a lot of your understanding of C or your confusion about C, particularly around pointers and arrays, from the perspective of what might be going on at a hardware level. And pretty much all processors have something like this. Now the way it works varies from architecture to architecture, but there's usually some way to do this indirect addressing. And this is the stuff that makes everything work, right? If you didn't have this, you can't do most of what we do with computers. You can't implement an array. You can't use the value of a variable to control what variable you operate on in some other operation, unless you wrote, 4 billion if statements. So this is fundamental to computer architecture, and you'll bump into this again and again in a lot of different forms. Okay, it's like mathematical induction in CSE 215. It'll keep coming up again and again. Main thing I want you to know is FSR0H, FSR0L, INDF0, and LFSR to load those two values. If you understand those, the rest is just extra detail. All right, so let's look at homework. So write some PIC code to use FSR0, HNL, and INDF0 to clear file register 0. You could just say clear F0, right? But I want you to do it using these file registers, okay, these special function registers. And if you're not sure if it works, write yourself some code in MPLAB, right? Set up by initializing file register to something 0 to something non-zero, and then execute your statements and make sure that it clears this file register. Okay, assuming you've just done 131 above, now write some additional code, right? after whatever instructions you wrote for 131 to clear file register 1. And think about the fewest number of instructions that you need to do that. And now write some PIC code that clears file registers 10 through 20 using INDF 0 and file select register 0, high and low. So similar to what we've been playing with in MP Lab. Now try to do this same question using POSTINC, PREINC, and POSTDEC. Alright, and then there's some analysis code, which is look at this code here and try to figure out what this does. So pretend you're a PIC processor and work through this on paper. Try to get a feel for what's going on. And then the last homework question of the entire homework set. Oh my gosh, it's exciting. 138, use Lfsr along with INDF 01, high and low, to copy 16 bytes starting from file register 40 to a block of memory starting at file register 80. So almost exactly what we just did. We went from 10 to 40. But think about this, right? Don't just copy what we were doing in MP Lab, but think about this and try to write it from scratch and run it in MP Lab and convince yourself that it works. Okay, so that's the homework. So it's going to be 131 through 138. And those are due Tuesday, but they're pretty short, I believe. We'll talk about floating point on Tuesday. I won't give you homework questions on it, but we'll talk about it. All right. Questions? There really should be tons of questions at this point.
Just to clear up the plus W, that happens before, not after, right?
So it doesn't change anything. So the before or after has to do with it's interesting in here because we're actually changing the value of this register, but we're not changing anything. So yeah, we add these together and we use that sum as the address of our operand.
Okay, so it
So yeah,
happens before
technically
the
before, right?
Okay.
I guess it would make no sense to do it after because we're not changing anything. We're not replacing anything with that sum. So yeah, it's got to be before. All right, other questions? All right, somewhere I have an extra sheet of ways to look at indirect addressing, I think. If I find that, I will post it up on Canvas. I'll post these question numbers on Canvas under homework 7, and that will be it for assignments, other than finishing up lab 6 and then the final exam next Thursday. So we'll meet on Tuesday. It'll probably be a long lecture. We'll go over everything else there is to know about assembly language and computer architecture, plus floating point. Bring your questions that you have on anything we've done in the course to class on Tuesday. We'll talk about it. I'd love to spend Tuesday just talking questions and answers. That would be most awesome. But barring that, I'll lecture on the remaining parts of the book. All right, well, have a great rest of the week. If you're off to WSU on Monday, have a fantastic start to your semester. And I will see you all on Tuesday or in lab hours in a few minutes. All right, thanks.